You're on a video call in a moving car. The bars on your phone flicker, then settle. The other person never heard a glitch. So, how does a live connection survive when your phone leaves one cell tower and joins another? That quiet handoff is one of the hardest problems in mobile networks. Radio coverage is local. Your phone must change which base station owns the air link. But the packets of your call still have to arrive in order, on time, as if nothing moved. If the network simply cut the old radio path and hoped the new one was ready, you'd drop frames, freeze the call, or lose the session entirely. Continuity under change is the real requirement. In LTE, one carefully choreographed answer is called an S1 handover. This lecture focuses on the execution phase, the moment the planned move becomes real. We'll watch control messages, temporary data bridges, and sequence state travel across the network so your call never notices the jump. Before any arrow fires, meet the cast. Think of a traveler leaving one train station for the next, while parcels still need a corridor to keep moving. The traveler is the UE, your user equipment, the phone. On the radio side sit two base stations, the source ENB, where you are attached now, and the target ENB, where you are heading. Above the radio edge lives the core. The MME is the mobility brain. It steers control signaling for attachment, tracking area, and handover decisions. The SGW, the serving gateway, is the local traffic hub that anchors user plane tunnels for your bearers. Farther toward the public network sits the PGW, the packet gateway, the door to the internet. In the diagram we'll rebuild, those 6 columns stand left to right. UE, source ENB, target ENB, MME, SGW, and PGW, with the internet beyond. Messages move as arrows between lifelines. Data paths are thicker pipes. Once you can read the columns, every later step is just coordinated motion across this stage. Handover is not one instant. The source diagram paints 3 colored phase rails so you never confuse planning with acting. First comes handover preparation, shown on a yellow rail. In preparation, the network asks, can the target accept this UE? Are resources reserved? Is the path set up on paper? Nothing has switched yet. The phone is still fully on the source. Then comes handover execution, the pink rail, and the heart of our screenshot. Execution is when the source tells the UE to go, when temporary forwarding is armed, and when the old radio attachment is torn down on purpose. After execution comes synchronization and resource allocation on a blue rail. The UE locks to the target, uplink timing settles, and final path switches complete. Here's the part that matters. Our source is labeled S1 handover procedure, execution phase. We are not redrawing the entire call flow from scratch. We are zooming into the pink band, where the planned move becomes irreversible action. Keep those 3 colors in mind: yellow plan, pink act, blue settle. As arrows start to fly, execution begins with a decisive message, the handover command. After preparation has reserved the target, the source ENB sends the handover command down to the UE. In plain language, the source is saying, leave me, and attach using the configuration the target already agreed to. The command carries the radio recipe the phone needs, how to find the target cell, which security and bearer parameters to apply, and that this is now an order, not a suggestion. Watch the direction. Control still flows from the network toward the phone at this moment. The UE has not yet proved it can hear the target. It has only been told to try. A common misconception is that the phone invents the handoff by itself when signal fades. In an S1 handover, the network orchestrates the move. The UE executes a command that the source delivers after the core and the target have already prepared the landing zone. So the first beat of execution is not data moving, it is authority moving. Source to UE, go. Now the continuity problem gets concrete. Downlink packets may still be racing toward the source ENB while the phone is about to leave. If those packets die on the old radio link, the call glitches. The network's answer is a temporary bridge, an indirect data forwarding tunnel. On the diagram, you see a create indirect data forwarding tunnel response and the creation of a TEID, a tunnel endpoint identifier, for indirect forwarding. A TEID is simply an address label inside a GTP tunnel. It tells the gateways which pipe belongs to this forwarding path, so packets can be steered without confusing them with the final bearer. Indirect forwarding means user data can leave the old path and be relayed toward the target side through the core, instead of requiring a perfect instantaneous radio cutover. It is a corridor for parcels while the traveler changes stations, not the forever home of the traffic. Hold that idea. Forwarding is scaffolding. It exists so execution can detach the radio without discarding in-flight data. Later path switches will retire the scaffold. For now, the tunnel response and the forwarding TEID are how the network says the bridge is open. The diagram refuses to treat data as one anonymous blob. At the bottom, it draws two distinct S1 bearers for indirect forwarding, one labeled DL, downlink, and one labeled UL, uplink. Downlink is internet toward the phone, video frames, web bytes, the other person's voice arriving to you. During handover, those packets may still hit the source side first. The DL forwarding bearer gives them a legal detour so they can be forwarded toward the target and then to the UE once the new radio link is alive. Uplink is the opposite direction. Your voice and acknowledgments climbing toward the internet. The UL forwarding path keeps that climb coherent while ownership of the radio edge is changing, so the core does not see a mysterious new stream with no continuity to the old one. Color and arrow direction matter here. If you collapse DL and UL into a single vague data path, you miss why mobile cores carefully maintain separate tunnel state per direction. Congestion, buffering, and sequence handling are not symmetric. So when you read the execution diagram, read two bridges, not one. Same idea, temporary continuity, applied in both directions along the S1 user plane. With the command issued and forwarding armed, the source must let go. The diagram marks detach from the source ENB. Detach is deliberate. The old radio connection is released, so the UE is no longer expected to serve two masters at once. Resources on the source can begin to free. From the phone's point of view, attention swings to acquiring the target. Here is the misconception to crush. Detach does not mean the network throws away the session. The session lives higher up, in bearer contexts, security context, and gateway state. Detach is a radio edge goodbye, not an identity wipe. If detach happened with no forwarding and no state handoff, in-flight downlink could vanish and the target would not know how to resume cleanly. That is why detach sits in the middle of execution, surrounded by tunnel setup and status transfer, rather than as a lonely cut. Plain restatement, the source stops being the phone's radio home, on purpose because a prepared target and a temporary data corridor are already in place. Changing the radio endpoint must not reset the story of the byte stream. That is why the diagram includes SN status transfer, sequence number status transfer, from the source side toward the target path. Sequence numbers are the bookmarks of reliable delivery. They answer which uplink packets were already received, which downlink packets were already delivered to the UE, what should be forwarded, retransmitted, or skipped so the receiver does not see gaps or duplicates as chaos. Status transfer ships that bookmark. The target learns where the source left off. Forwarding can then prefer the right residual packets instead of guessing. A first-time learner often thinks handover is only about signal strength and cell IDs. Those matter in preparation. In execution, order is a first-class citizen. Without sequence status, a perfectly strong new radio link can still deliver a jumbled application experience. So after detach, the network does not merely hope. It tells the next hop exactly how far the conversation had already progressed. Continuity is not only connectivity, it is continuity of sequence. On the right of the source figure sits a small topology box labeled Same SGW. It is easy to skip. It is also the quiet reason this handover stays organized. In this scenario, the serving gateway does not have to change when the UE moves from source ENB to target ENB. The radio edge pivots. The local user plane anchor can remain the same SGW. Bearer paths rearrange around that stable hub. Old S1 legs, forwarding legs, and eventually the new S1 leg to the target. Why does that help? Because a large fraction of mobility is edge mobility. If every cell change also forced a full rebuild of the core anchor, handovers would be heavier, slower, and more failure prone. Keeping the same SGW localizes the surgery to the places that truly moved. Be careful with claims. The diagram shows a same SGW case. It does not prove every handover keeps the gateway. Other procedures exist when anchors must relocate. For this execution picture, the takeaway is architectural calm in the middle of radio change. The internet-facing side can stay steady while the last-mile radio ownership flips. The traveler changed stations. The regional sorting facility stayed put. Let's walk the execution timeline as one continuous story, the way the sequence diagram is meant to be read. Start on the pink rail. The handover command leaves the source ENB and reaches the UE. At that instant, the phone still has its old radio home, but it now holds the recipe for the new one. While that command is in flight or just after, the core finishes arming the scaffold. The create indirect data forwarding tunnel response confirms the bridge. Tunnel endpoint identifiers are minted so downlink and uplink forwarding pipes are unambiguous. Next, detach from the source ENB. The old airlink is released. Attention shifts to the target. Forwarding is already there, so packets that would have died on the old link still have a legal detour through the SGW region. Then SN status transfer moves the bookmarks. The target learns the sequence story, what was delivered, what remains, what must not be replayed as noise. Throughout, the bottom of the diagram keeps two S1 bearers for indirect forwarding in view, DL and UL, reminding you that user plane continuity is directional. And on the right, the same SGW inset explains why this choreography can stay local. Radio ownership flips. The serving gateway anchor need not. If you remember only one animation, remember this chain. Command, arm the bridge, detach, transfer sequence status, keep DL and UL distinct, prefer a stable SGW when the diagram shows one. That is the execution phase as a single motion, not a pile of unrelated acronyms. Zoom out and retell the argument in one breath. A UE must change base stations without dropping the living session. Preparation reserved the landing zone. Execution delivered the handover command, opened indirect forwarding with tunnel endpoint identities, separated downlink and uplink bridges, detached the source radio, and transferred sequence number status so order survived the jump. Through it all, a same SGW topology can keep the core anchor stable while the edge moves. This is larger than LTE trivia. It is state transfer in a distributed system. Move the attachment point, preserve the session, bridge in-flight work, and hand off the bookmarks that make streams coherent. One open question the same style of reasoning can attack next. What extra coordination is required when the old path cannot be maintained? When forwarding fails, when the SGW must also move, or when the UE never successfully attaches to the target? The execution phase we studied is the happy, carefully scaffolded path. Real networks are judged by how they behave when the scaffold shakes.